Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. Well, good morning, good afternoon, good evening, depending where you guys are today, because we truly have an international session here today. For example, I am based in Spain, our two speakers are based in the US, and I'm sure many of you are based all over Asia. So it's different times in different places, but this is the great thing about these webinars, that we can actually get to share knowledge across borders, in many different markets at once. So welcome everyone. I would invite you guys to introduce yourselves, your companies, and where you're joining from today in the chat, so that we can all see, so other people can see it. Make sure that you tag everyone so that we can all read it, and let's get to know one another, so that these sessions can be not only for us to, to be talking and learning, but also to maybe meet other people that we might be interested in. So here we are. Okay, today we're talking about the complexities of designing PV projects in high wind regions of Australia. Seems really simple, doesn't it? You look at a great solar area, a great solar land, you measure the sunlight for like a year, you figure out there's going to be great returns, and you forget to actually check on the wind and seeing actually what this means in terms of how you should design your project to make sure that it's resilient to especially in high wind areas. But however, technology to the rescue, the technology has improved leaps and bounds, and actually things are changing very quickly, and there's a lot of technologies and also designs that can help you actually optimize your project, the area that you're using, and so on. However, I am not going to talk to you about this because my knowledge on this is limited at best, but I do have two experts with me today who are going to share with you their knowledge in this area, and I'm going to ask them to introduce themselves so that you get to know them a little bit, even though you're already seeing a little bit about them on the screen. But Yarrow, please, if you could introduce yourself.
Yeah, my name is Yarrow Fewless. I'm a principal at CPP Wind Engineering Consultants in the United States. And I've been with the company for 17 years, but working on solar structures for about the last 10 or so, quite intensely.
Thank you very much, Yarrow. And now, Scott, please, if you could introduce yourself.
Morning, good evening. I'm Scott Van Pelt, Chief Engineer for Game Change Solar. I've been in the renewable industry since 2010, and I currently work as the Chief Engineer for Game Change, overseeing all of our technical deliverables.
Excellent. Well, thank you very much, both Scott and Yarrow, for introducing yourselves, and thank you very much, everyone in the audience. Now we begin, and here is how it's going to go. It's very simple. Today, we're going to have a presentation first by Yarrow, then we're going to have one by Scott, and then we'll take some questions at the end, okay? How you send us the questions is you use the Q&A box at the bottom of the screen. Don't use the chat. The chat we use to chat amongst ourselves, but for us to be able to manage the questions properly, please send them through the Q&A box. Don't worry, we will be reminding you. And just a couple of reminders more so that you know. If you're on YouTube, just please drop your question in the box, and we will make sure to bring it over here to ask the speakers as well. So even if you're on YouTube, don't worry, we will take your questions, okay? And we are recording this session. It will be available thereafter. And also you'll have access to the materials, so you don't have to worry, because you're definitely going to be able to see the video again and to check the materials or share them with your colleagues if you're so inclined. So without further ado, I'd like to ask Yarrow to please share your screen and prepare for your presentation. And we will just launch into it, because this is going to be 1 hour well spent of your time. Believe me, you're going to leave with a lot of knowledge and the right people to contact if you have any questions on this specific topic. If you can put that in full screen, please.
I thought I was.
No, we're seeing around the presentation around. I think if you press the little presentation icon at the bottom of the screen next to the Zoom. Oh, there you go. Perfect.
Don't know why everything works well in practice. All
yeah,
right,
one of them things. Let's go right ahead. Thank you, Yarrow.
All right, you're welcome. Thanks for the introduction. So Scott and I are going to cover this topic today. I am going to cover the sort of wind loading aspect of it, what the wind does to the structure, and Scott's going to talk about how to handle that. So I'm just going to jump right in here. I've already given a brief introduction of myself. If you want to read that, you can watch the video back. The company I work for is CPP Wind Engineering. We're based in the United States, but we have an office in Sydney, Australia as well, a pretty significant office in Sydney. And we focus on wind effects. I personally focus on wind effects on structures, and that's a bit more than half of our business is wind effect on structures of all different kinds, starting with tall buildings, but as of the last 10 years, shifting a significant part of our company to working with developers of solar racking systems. One of our biggest tools as wind engineers or wind engineering consultants is the wind tunnel. And I'm showing an image here that shows a rendering of the wind tunnel and then an image from the inside of a test model. This is a specific type of wind tunnel that I'm going to talk a bit about, and I'll talk a bit about the models as well. But it's designed for capturing or measuring loads and pressures on small scale models of structures. Again, it started with tall buildings, sky-rise buildings, some of the tallest buildings in the world. Well, all of the tallest buildings in the world have been tested in this type of tunnel. But now that same tool is being used for the testing and design component of all manner of solar racking. There's other parts of our business that are related to solar that are outside the wind tunnel, such as estimating damping or helping clients estimate damping, or coming up with site design wind speeds when the wind map isn't good enough. And I'm going to touch on some of that in more detail. So let's start with a general summary of the challenge of designing for wind. It's kind of three parts. One of them is specific to single axis trackers, but everything needs to get the first part right, which is the wind excitation. What does the wind do to the structure? And did your wind engineer, your expert on wind loading, use an appropriate state-of-the-art technique to simulate the model in the flow simulation and in the analysis as well, so that you can trust that the loads are coming out are correct? There are standards for this, so I'm not going to talk a lot about how to do that correctly. The next step would be, all of these structures vibrate in the wind. All these, solar racks, ground mount, whether they're fixed tilt or trackers, they vibrate in the wind. And to predict how it's going to vibrate, you need a finite element model. If you have that, that's step one. You need to make an estimate of what the damping is going to be on the system. Before you have a prototype in the ground, both of those things are sort of best guess. But really, it would be good to get a prototype in the ground so you can benchmark your finite element model and actually measure damping on the system. Then you have these, with some accuracy. And with all of that, then we can predict what the dynamic response of the structure would be to that wind excitation. And then the last one, as I mentioned, is for single axis trackers. Is the system going to stay stable at the design wind speed? Because it doesn't matter if you put all your effort and accurately account for the wind excitation and how the structure vibrates to get the dynamic response. If you haven't designed it for stability, you will be surprised to see a single axis tracker can go unstable at a very modest wind speed, well below the design wind speed. And so with those 3 points, I'm going to go into a little more detail. First, I'm going to talk about the wind tunnel, just in brief, so it's understood what kind of a tool we're using here. I call it a wind tunnel. It is truly a wind tunnel. An aerospace wind tunnel where you would see airplanes and whatnot tested, they're not actually wind tunnels. They're simulating an object moving through still air. So they have different criteria than we do. We're actually simulating the wind, and at small scale in this case. So our purpose, or the goal of this wind tunnel, is to get the appropriate turbulence characteristics modeled in the flow inside this wind tunnel and at a scale that's appropriate for testing some structure. This is inside the wind tunnel. The photo here looking upstream from this, if you can see my cursor, the circle right here through the window would be where the test model goes. Looking upstream from that, you see this fetch. The floor is covered in all these block elements, and then there's some more elements on the upstream end. With flow coming toward you, the viewer, it passes over all these objects and generates turbulence of different scales, which sort of combine. And by the time you get to the edge of the turntable model, the solar model in this case, you have developed the right turbulence characteristics for the scale you want to test at. I don't want to go into any more detail than that, but it's a critical parameter that this is the type of tunnel that is used for wind loads, because if you don't have the turbulence right, if you don't have the gussiness right, the loads can't be trusted. They have no basis. So taking the step back with this photo, just moving back just slightly, so now you can see the test model in that same general section there. This is a model of a single axis tracker. It's a pressure model, and I'm going to talk in detail about that. It's mounted on a turntable that is just like a record player, only it spins very slowly. So you can turn the model to simulate the wind at increments suitable for capturing all the behavior of the variation of loads with wind direction. A model like this had around 800 pressure measurement locations on it, on the upper and lower surfaces of the PV modules. And then from that, we can do an immense amount of analysis, immensely flexible, I should say, to come up with a suitable number of load cases for the designers to use. The instrumentation, that is the pressure measurement hardware, is all mounted under the floor of the tunnel, so you don't see it in here. It's all hidden from the wind. So 3 model types. I'm going to focus on 2 of them because one of them isn't used all that much anymore. The top one's the pressure model. I just talked about that a little bit, and I'll go into some more detail. The middle one, the high frequency balance model, is it's a way to measure the overall loads on a structure without having to integrate pressures. Where the pressure model, you need to integrate. That's both a strength and a weakness, because you need to integrate, so you have to have enough pressure taps. But if there's finer details, or if you have issues getting the pressure taps into the model, those are the measurement ports, then you have to switch to something like the high frequency balance model method, where you can get all the geometry right and just measure the load directly. The drawback of that method is that you're getting a few components. You're getting shears and moments. You're not getting detailed load distributions. The only time we've used that, or the most frequent time for solar when we've used that, is for heliostats and dual axis trackers, where it is difficult to get the pressure measurements into the model without distorting the flow. And then the last one, the aeroelastic model. This technique has been around for many, many years, from tall, slender buildings. But the phenomenon that requires this type of model is something that's fairly unique to solar, which is an aeroelastic instability. When I say aeroelastic, I should define that. It's an aerodynamic effect that is changed by the movement of the structure. The structure flexes enough that its movement can alter the flow going around it. And when that happens, a rigid model type like a pressure model, it has questionable value, or it has sort of baseline value, but once it starts to move enough, you really want to get some better values from a model that more properly simulates that movement. And I'll have some more detail about that as well. But the bottom line of an aeroelastic model is that it does flex in the wind tunnel like the full system flexes in the field. And so whatever we measure directly. So detail on the pressure model. This is just a zoom in on the end of one of those rows of the pressure model. It is, the tap pair there is circled in black. And it's just a pair of these pressure ports, one on the top, one on the bottom, and they're channeled off to the side and then routed out through the bottom of the model to measure the pressure at each location. And you do that on 100 plus locations per tracker, rack, whatever you're looking at, and you can integrate over the whole area. In post-processing, you can collect that in the wind tunnel simultaneously, all the different taps, and then post-process it in any way that you should need for your specific system. So here's just a quick graphic, a little video showing some fluctuating pressures from a wind tunnel study. In this case, it is a 20-degree tilt with the leading edge into the wind, up into the wind. So it's generating high suction values. Those are the warm colors, the reds and oranges. It's a cornering wind, slightly cornering, 20 degrees off of normal. And so you do see, a specific concentration down along the south edge there and along the leading row as well. We would generally collect data in 10-degree increments. And depending on the requirements of the system, you would want to look at different tilts, heights and GCR, depending on how much those parameters vary. But when you combine all those things, getting enough data in the wind tunnel for all the wind directions, all the heights, tilts, and GCRs that you need, you can end up with over 100 billion data points, just this raw data. It's a mountain of data, and really the analysis is where the fun starts as far as coming up with useful load cases. So just dwelling on that for a moment before I get into the analysis, showing a bit about how that varies with wind direction, because I showed a cornering direction before. In this case, it's a little bit steeper tilt, 45-degree tilt, leading edge up into the wind. So again, it's generating suction pressures. The wind direction really matters as far as what the pressures are. That cornering case in the top plot there is the high loads are, well, they're basically the highest of any direction. They're very concentrated right at the end of the row. And there's quite a significant reduction as you get to the interior. As that angle, that wind angle changes closer to perpendicular, you can see that cornering effect dying off. And I should mention that cornering effect is due to a phenomenon known as a corner vortex. And for a cornering, when you end up with two of those little vortices, they look a bit like a little tornado laid down flat against the modules, sort of with the long axis parallel to the modules. And so they create tremendous suction right on the module surface, but they form right at the corner and they die off reasonably fast. So they are intense, but they die off reasonably fast. In the bottom plot, you can see what the wind looks like when it comes straight in. And that edge effect, the cornering, the vortices have all but gone away, and you really have a more even pressure along the whole row, which is also less severe. It's just not as severe of a load at that case. And that type of high suction is just due to flow separation off of the sharp edges of the modules. So what can we do with all that data? So this is looking at that model again, one of those tracker models that I showed earlier, and just overlaying some colored pressure patterns. The color corresponds with the magnitude. So the brighter red means a higher intensity pressure. In this case, the red is a positive pressure, or one acting down toward the earth. We take all that data and we can slice it up into smaller areas. For this load case, we might be interested in the peak load on a module for design of the module, or for design of the module mounting to the torque tube or to the racking, depending on what the system is. And when we go through all of the time history of the configurations and the wind directions, we come up with this load case that maximizes the peak load on the module. You can see it's, well, the intensity is bright red, which in my scaling means highest pressure. It's also relatively even. It's asymmetric, so there is definitely a gradient from the leading corner to the, which would be the lower corner in this case, to the higher corner. There's a bit of a drop in pressures, but it's pretty high everywhere. If we then wanted to look at the load on a post, our area would increase. We're looking at a broader tributary area. And now we're filtering through that time series, looking for the peak load on this larger area, that first post and its nominal tributary area. And what we see here is that the instant in time that maximized the load on the whole post was not the same point in time as the one that maximized the module. And it may not even be the same wind direction. And the red actually came down considerably in intensity, indicating the pressure was less. I can go back. So there's the module pressure, bright red. You go to the post pressure or the post load, and it's less red, less intense, both on average and in the most severe part of the area. It's not as intense. We can extend that even further for single axis tracker, and you can see this time quite a stark drop in the sharpness or the brightness of the colors. There is still a little hot spot near the corner, indicating that there's some sort of perhaps a vortex forming along here. But by and large, this half tracker area, in this case, we're looking at a half tracker moment. So maybe design of the torque tube or design of connection to the drive system or something. At this particular moment, when moment was maximized, it's probably a different direction. It's certainly not as intense at the corner. It's really the one that makes that biggest asymmetric load that would be of concern for the design of those torque tube type components. So then we've captured all this data from the wind tunnel. That is, a nominally rigid model in the wind tunnel. This is the excitation, as I'll call it, which is what does the wind do to the structure? So the question then becomes, how does the structure respond? Does the structure vibrate in a way that is meaningful? And I'm sorry about all the text on here. I'll try and talk you through it. So every structure vibrates at some frequency. If it's high enough, you don't necessarily need to worry about it in terms of amplifying your loads. But if it's at a low enough frequency, the excitation from the wind can be amplified by that vibration, and that energy gets fed into the system at the natural frequency of the system, and can actually increase the loads based on the inertia just of the system vibrating in the wind. So I want to talk a bit about the wind turbulence spectrum and how that lines up with the structure. But ultimately, you have this broad spectrum of energy in the wind. You have the effect of the rack itself, perhaps shedding vortices, which is a very interesting phenomenon that I'm going to show a little bit more of. And then how does that combine? How does that turbulence spectrum with that vortex shedding energy combine or overlay with the natural frequency and the tendency to want to vibrate of the structure at its natural frequency? When it does, when that amplification or when that energy is amplified by the vibration of the system, we just call that dynamic amplification. And it can be really significant. In fact, I think all the major international wind loading standards now are coming to realize that the old criterion, which was 1 hertz, not that many years ago, they had this 1 hertz criterion in the code. They've all started to adapt to higher criterion, usually 5 hertz or more, with this understanding that people are designing smaller structures that are more sensitive to this high frequency energy. And not only are they more sensitive to high frequency energy, they're generating high frequency energy. They can self-excite. That vortex shedding that I'm going to show you is a phenomenon that the modules generate, but that also affects and loads the modules themselves. So with that in mind, I think this is probably the most technical graphic that I'm going to show you. So I'll try and walk you through it. These are spectra of the excitation on the left. Let's focus on the one on the left first. So spectrum of the excitation of the first row of a 30-degree tilt tracker, let's say. So it's leading edge up. It is going to shed vortices off that leading edge, and they're going to alternate leading edge, trailing edge, leading edge, trailing edge in an organized fashion. And that's going to produce a spike in our spectrum, which is exactly what you see here. The sort of orange dotted line or dashed line that I drew represents what the approach wind looked like. And the blue line represents the spectrum that was measured on the tracker, in this case, on that first row after the wind passed over it. So it's exhibiting strong vortex shedding. This plot shows how that energy, the y-axis is energy, shows how that energy varies in frequency. And in this case, I've normalized it by some hypothetical system with a natural frequency f naught. I think I used 2 hertz in here, but it's not necessarily relevant. The spectrum of the wind shifts left and right depending on the wind speed. The faster the wind speed goes, the faster that turbulence reacts. And so everything that happens at a certain wind speed will shift up as the wind speed shifts up. So this particular case on both sides of the screen here is for 8 meters per second at 10 meters, which is quite low, an everyday type of wind in many seasons. when you overlay the response of the system on there, and I said this was technical and I apologize for that. When you overlay the response of the system on top of that, you get this orange line. And this represents how the vibration of the system can add energy into the spectrum of loads. In this case on a torque tube. I think this was a torque tube moment. But there's a considerable spike here where the natural frequency is. Luckily though, it's at a lower energy part of the spectrum. It's kind of down here where it had already decayed considerably from the highest energy part. But it is still significant. It's not horrible, but it is still significant, with the reminder that this is a logarithmic plot over here. So every major division is an order of magnitude more energy. You know, it's a narrow spike, but it is exhibiting or introducing vibration with enough energy at in this narrow band that is significantly greater than even the vortex shedding was. The next slide, I'm just going to take that same example, and it's going to be a video that shows how the wind spectrum slides over as the wind speed comes up. So in the top, a design level of event, a pretty significant design level event. And as the wind speed goes up, that wind spectrum slides over, and that vortex shedding eventually matches the frequency of vibration. And at that point in time, if you can follow the logarithmic scale on the left, that spike is almost 3 orders of magnitude higher, 1,000 times higher than anywhere else in the spectrum. So this is when you get significant dynamic amplification. Again, it's a narrow spike with respect to the whole spectrum, but the amount of energy in that narrow spike is really significant. So this is a really fascinating concept. I hope at least you get the fundamental of this, this part of it. I know the spectra are a little bit hard to digest. The next one here. Last thing I'm going to talk about then after that dynamic response is stability. And again, this has to do with single axis trackers, because most of the other types of racking systems don't have the flexibility that a single axis tracker can have. You go back a number of years, 7 to 9 years, and single axis trackers were this novel way to get more energy, but nobody had really built a lot of them in the field. So people hadn't experienced sort of how much the systems could flex. And as they got built, people started to experience or recognize that these were deflecting a lot in the field. And when I say deflecting, I mean torsionally. So they're twisting about their length. You have a long wing and you have a long torque tube with modules mounted to it. And if you do all the static and dynamic calculations right, you still end up with a lot of twist at the end of this long row. And what ended up happening was a phenomenon that resembled some phenomena that had been seen before in bridges. In other industries, it would have been called flutter or galloping, but it didn't behave quite the same. It's a new phenomenon, a new instability called cyclical torsional divergence. And this is, I think it'll be easily understood from some of the videos I have here, but I want it to be understood that it happens at low tilt. This is the first of 2 instabilities. This one happens at low tilt. The basic phenomenon is that the leading edge sheds a vortex, and that, or it forms a vortex which tips it up a little bit, sheds the vortex, and then crosses 0 to go below horizontal and sheds a vortex on the other side. And each time it sheds a vortex, I might as well press play on the video here. Each time it sheds a vortex, it deflects a little bit further. This is really a stiffness-driven phenomenon. So the problem here is that the system is able to deflect too much. And this simulation goes back quite a few years. It's probably 9 years old, 8 years old, something like that, from a system that was designed without consideration of this effect. And now we know about it. It's fairly well understood and studied now, so you can avoid this with stiffness, or in some cases you can avoid it with a very high extreme level of damping. But it is catastrophic, and it occurs at moderate wind speed, well below what you would expect for your, or based on the design level wind event that you're going to consider for static loads and dynamic response. The bottom video here is, it's an old video again. So this is one of the first instances that we were sent of a system going unstable like this in the field, getting a request from somebody who wanted us to help them diagnose, what this instability was caused by. And I'll just press play. This is a modest wind speed day. I've said that a few times for emphasis. It was a low tilt. I don't know if it was exactly 0 tilt, but it was low. It might have been a few degrees up into the wind. But it is a modest wind speed day. The person holding this camera was out that day working in the field, driving their truck around without concern for a high wind speed event. They're not falling over in a 40, 50 meter per second wind. This is moderate. This might be 20 meters a second. And I'm fairly certain that no one wants to see their modules getting yanked around like that. So that was sort of where it started, things like this from the field, and then starting to investigate it and coming up with a good understanding of this phenomenon, which again is stiffness driven. For the most part, you can control it with stiffness, which means either not having as long of a wing, or having intermediate drives or intermediate locks, or something along those lines to greatly increase the stiffness. The other phenomenon is the vortex lock-in. And this one is that term has been used in other industries before to convey that it's a vortex shedding phenomenon where vortices are shed from alternate sides of a structure, in this case, the leading and trailing edge. It happens when the tilt is not near 0 for solar structures. 20, 30 degrees tends to shed vortices pretty strongly. And that one is not as much stiffness driven as, it's a lock-in of the natural frequency with the shedding frequency, but it is more controllable by damping. You can control it more easily with a decent level of damping. And so just last kind of topic on the testing side of things is the aeroelastic model I touched on. This is the one where you simulate the mass and the stiffness correctly and the damping all at model scale, so that you can recreate the behavior in the wind tunnel that you expect in the field. And this is the most sophisticated type of wind tunnel model for structures right now. The primary interest for solar is that torsional mode. So we spend the most amount of time on these, trying to model that torsional mode of vibration. You can also model the heaving modes of vibration if that's of concern. And you can get quite a lot from this model, but fundamentally it came about to try and characterize that instability phenomenon and find ways to get past it so you could have a system that stayed stable up to the design level. One last slide on the effective large format modules. I don't know if Scott will cover this in more detail or not, but there are a couple of notes I'd like to make on it. For loads, it's fairly simple. You go to a larger module, you increase the area, loads go up with area. Moments also go up with area, but if you're making the chord length of the system bigger, you're also increasing the moment arm, so moments will go up as well by the same proportion. So a 20% increase in module area would be 20% increase in loads, but 44% increase in moments. There's other smaller parameters like post spacing that might get altered as you go to a larger module that can affect the coefficients. If you make your posts closer together, you can increase the correlation and increase the coefficients a bit as well. So there can be a bit of a double whammy there. In the dynamic response side of things, the damping ratio is reduced because the critical damping gets increased due to the increase in mass and stiffness required for these bigger modules. And when damping ratio goes down, the dynamic response tends to go up. In that slide I showed with the orange spike in the spectrum, that orange spike will get worse for a lower level of damping. It'll actually get taller, higher up in the spectrum, higher up in energy. The dynamic amplification factor can improve slightly. If the mass and the stiffness both increase, the natural frequency stays about the same, but the bigger chord means it sheds the vortices at a lower frequency. And so you actually have to have a slightly higher wind speed to get that to line up. So that can be a slight improvement. It's not offsetting, but it can be a slight improvement. And under the torsional instability side of things, that reduction in damping ratio is notable again. But beyond that, the effect of these combined variables of this, the chord size and the change in stiffness or frequency and the damping ratio, combined with the fact that the perimeter rows affect what happens in the interior. So deflections of the perimeter rows really matter when it comes to what's happening in the interior. It just makes it too hard to give any sorts of rules of thumb as far as torsional instability is concerned. And so just summarizing here, last slide, the three concepts for the challenges related to wind design, maybe the static loads, that's the excitation that the wind applies, The dynamic loads is an analysis component usually of that excitation that tells you how the system vibrates in the wind. And both of those are assuming that the system remains stable. And then the last one is the instability, which I've just gone through in depth there, but the other studies don't really matter if your system doesn't stay stable. So it's a really critical thing to get right. So the system actually makes it to that design level intact. And I think with that, I'll hand it over to Scott.
Thank you very much, Yarrow. It's always good to see, that how much detail, how much analysis, how much study there is, for every single item effect, parameter that the wind adds on trackers and structures. They have to withstand so many years and so many rough conditions sometimes. So thank you very much. A lot of detail out there for the techies. I'm sure you guys really enjoyed this presentation. Don't be shy and send the questions through, so that we can get to them. I also have a couple of questions myself. And next, I'd like to ask Scott to please share your screen and start your presentation. And, at the end of the day, with wind, the tracker and the structure is the bottom line, isn't it? So you have to make sure that if other components you're going on the chip, maybe think about it when it comes to the tracker, because you just heard, everything that can happen to your trackers. So go right ahead, Scott.
Great. Thank you, Yarrow, for queuing that up. It's been a pleasure working with CPP for last few years. So I'm Scott Van Pelt. I'm the chief engineer at Game Change Solar. I'm a licensed professional engineer here in the States. Been working in solar since 2015. Was working doing wind turbines for several years before that. Have a fair amount of experience designing racking structures both stateside and around the world. And I've worked on several IEC and other national committees. So Game Change Solar, we are a fixed tilt and racking designer, and we procure those systems. We do it at a large scale, and we do it around the world. So currently on 6 continents. Including in Australia. We just wrapped up a 106 megawatt fixed tilt project. We do a lot of work in hurricane and cyclone prone areas. So the Gulf Coast of the United States, Western India, numerous locations where we have to deal with high wind speeds. So we're intricately involved and knowledgeable on some of the concerns and some of the maybe atypical things that should be considered when designing for a cyclone-prone region. So I'm going to divide my presentation up into 2 segments. I'm going to talk a little bit and build on what Yarrow was talking about in terms of what are our concerns. There'll be a somewhat lengthy discussion on kind of how do we take the wind speed and convert it into forces and pressures on the components in the structure. I saw from the chat there are a couple structural engineers on the line, so hopefully that's not too dull for you all. Hopefully that's well understood. And then we're going to talk about some of the different solutions that we have. So what are the levers that we have to pull when we're designing a fixed tilt or a tracker structure to accommodate some higher wind speeds and higher wind pressures. So starting with the code. So as most places, Australia has a code that encompasses wind speed. 1170 is very useful. As you can see in the figure on the left, that's from the Australian standard. And really, when we talk about cyclone-prone regions, we're talking about wind regions C and D, so along the north coast. The figure on the right is also from AS 1170 from the Australian code. And this dictates what are the design wind speeds for the different wind regions. And I've highlighted that row for V50. So typically, tracker structures are designed to a 50-year return interval in Australia. And that's, for the structural engineers of the line, it's table 3.3 of 1170. It's for an importance category 1 structure. And you can see there as you move from the non-cyclone prone regions, A and B, to the cyclone prone regions of C and D, there's a dramatic increase in wind speed. So these are areas where where certain special requirements may be imposed on the tracking vendor in order to accommodate those higher wind speeds and higher wind pressures. So I want to take a couple minutes and talk through kind of the relationship between wind speed and force or pressure on the racking structure. So this is the appropriate formula for that. The equation number is 2.5 out of AS 1170. And just breaking it down, so the first clause is just straight from the drag equation from aerodynamics, right? 1/2 the density there. The next clause is wind speed. And so you'll see that that's squared. And so the forces and pressures on the racking structure are particularly sensitive to the wind speed. Probably isn't a surprise, but it's useful to keep in mind that it's a squared function, it's not proportional. So those racking structures that are being designed in wind regions C and D are seeing dramatically higher wind pressures than those in the interior of the country. So keep moving through the formula. What's actually most interesting to us as the designer of a racking structure is the shape factor. Using the American parlance, it's called the gust coefficient. So this is what's actually taking account for the geometry of the structure. And not surprising, a Lamborghini is a lot more aerodynamic than a billboard, right? This is the part of the equation that takes account of that. In the newest version of 1170, the code actually includes shape factors for ground-mounted and roof-mounted solar arrays, which is fantastic, right? It's very encouraging to see the standards community in Australia including this sort of information. One important note, though, is whenever tables like this are included in a standard, and be that 1170, be it Eurocode, be it ASC 7 in the States, these tables are envelopes of the worst case options that are aware to the standards writers. Right? So they're going to look at what is my worst case GCR, tilt angle, et cetera. And they're going to publish the highest shape factors that encompass all those worst case scenarios, right? This is not specific to a given racking or tracker vendor. So this is one of the big ways that we see to bring wind pressures or wind speeds down is using actual wind tunnels testing to derive these shaped factors. And that's kind of what Yarrow talked through a little bit already. But again, great to see that it's in the code, and this is the way that standards committees in Australia are moving. So I'll touch on this very briefly, right? Yarrow went into good detail about the wind tunnel itself. Section 1.1 of 1170 does make reference to use of wind tunnels for determining shape factors. And simply put, by using the models in the wind tunnel that are specific to the game change tracker or any tracker system, Next Tracker, ATI, et cetera, you're going to get more specific, more accurate, and less conservative, in other words, not overly conservative shape factors. That's going to make the design more economical and more practical for a high wind zone. I'm just rounding out this equation. So the next factor is for the dynamic amplification, which Yarrow touched on already. And lastly, area. And I bring this up, it's kind of obvious, but currently there's a move within the solar panel manufacturers, different manufacturers of the PV modules, to go what's known as a large factor, move to a larger form factor. And so these modules, typically they're about 1.3 meters wide, right? As you go from a conventional shape module to a large format module, you're increasing the area, you're going to have more forces on your bolts, more forces on your mounting rails. And so it's just something to keep in mind if you're a developer, you're sourcing modules for a project, if you're in a cyclone-prone location, can the mounting structure accommodate that larger force? All right. So to round out kind of the concerns part of my presentation, this dovetails with what Yarrow was talking about. This is the aeroelastic testing. So I'd like you to keep watch of the table there on the left. The wind is coming from left to right in this image. So on the left side is the leading table, and you'll see the table momentarily will lose aeroelastic stability. So this, as you can see there now, that this wild back and forth motion, I think Yarrow showed an image from the field, but we do actually see this in the field. Recently, we had an installer forget to couple one of the tube segments together to the motor, and the system did go unstable and moderate winds. So this is not an exercise. We do see this in the field, as Yarrow's clients did in the older video that he showed. These are kind of the things that we're looking at when we're designing a racking system in a higher wind speed environment. Is, are we maintaining elastic stability? Do we have enough capacity for the modules? And so those are the things that we're mostly looking at. So starting to talk through, okay, how do we address this? What are the tools in our toolbox as designers to create an elegant design, cost-effective design? So the first decision is really, what tilt angle are we going to design the tracker for? When the tracker stows or goes into its defensive position, what is the tilt angle of that structure? And kind of there's two different philosophies. There are trackers in the market that will stow flat. The advantage to that is there's less pressure on the face of the modules. The major detriment to that is that there's a higher torque on the torque tube, and they are much more susceptible to air elastic stability. So in other words, the wind speed that's required to get that dramatic motion back and forth is much lower. Alternatively, you can stow at a relatively high tilt angle. This will result in higher pressures on the modules, but the trade-offs or the advantages are lower torque on the tube and more air elastically stable. Given the, kind of as Yarrow pointed out, given the catastrophic nature and binary nature of air elastic stability, we typically find that that's going to govern. So Game Changer's approach is to stow at a higher tilt angle and to accommodate those higher normal pressures accordingly. So, okay, so we figured out our tilt angle. We're designing for air elastic stability, but we've got this high pressure on the modules. So how do we accommodate that? So solar modules are typically designed for a mechanical capacity of 2,400 pascals. And recent changes to standards make it possible to even be less than that. Right, so module vendor A can go to TUV or Intertech, or in the States UL, and get a test report or listing per the applicable standard, IEC 61215, for say 1,900 pascals or something less. And that may or may not be appropriate for a project in a cyclone-prone region. So again, developers, EPCs, as you're selecting what module to use on your project, the mechanical capacity of the panel is something to keep in mind if you're designing in wind region C or D, something that's cyclone prone. On the flip side, even though the module is rated for 2,400 pascals, that's not necessarily all the module can handle. Right? And there are ways that the racking vendors can work with the module manufacturers to increase that rating. Can the racking vendor provide longer mounting rails? Can we bolt to the module at 8 locations instead of 4? So there are a couple of tools in the toolbox that can be used to increase that mechanical capacity to 3,000 or even 3,600 pascals, to the point where now the mechanical capacity of the system is shown to be enough for that high wind event. Again, the testing is done per the IEC 61215 standard. It includes safety factors and includes a whole bunch of tests, not just visual inspection, did the panel crack, but electroluminescent and infrared testing. There's an image there on the right of some infrared testing to confirm that the panel is not damaged electrically, in addition to not being damaged structurally due to that high wind pressure. So to continue to flesh this out, so the capacity of that system, it really is a system, it's an assembly. It's both the PV module and the mounting rail. So higher mechanical ratings can be achieved by using longer rails, mounting at more locations. For projects in the interior of the country, if you're down by Adelaide, you may be able to use a clamping system. Again, Game Change, ATI, Next Tracker, the typical tracker vendors do all supply. They all supply clamp type systems for mounting rail. More economical, quicker to install. Typically don't have the mechanical capacity to be appropriate for a hurricane-prone or cyclone-prone region. But typically you can provide enough rail and stiff enough rail to reach a mechanical capacity you need for those higher pressures, in particular if you're using more than 4 bolts per panel. Last note is to look at the height of the panel frame, right? So the panel frame itself, there are module manufacturers that are coming out with module frames that are only 30 millimeters high. They tend not to be as strong as modules that are in 35 or 40 millimeter frames. Quick note on different module types. Bifacial modules are pretty common at this point for utility scale systems. They do tend to be a little bit less strong than their monofacial counterparts due to the lack of a backing bar. And for the large format module, again, there are times, particularly for the large format modules, these 1.3 meter wide modules, where the glass itself cannot support the pressure that's required for a cyclone location. And that image there in the bottom right is the case where the glass literally fell out of the panel frame, despite the fact that the panel was supported at 8 points. So selection of module when you're working in a cyclone-prone region is very important. One last note on module testing. One of the things that Game Change does track is deflection of the module itself. This is really relevant for the downforce case. There's not a ton of snowy locations in Australia, but for the work we do in Canada and Northern North America, the concern is that the junction box of the module will come down and kiss the road tube. We'll actually have a geometric conflict with the road tube under loading. So that's one more thing to just be aware of, and that the designer should be keeping track of. So in terms of our mitigation options, this is one system that Game Change has, a tool in our toolbox called a porous panel. So this is a patent pending system. The idea is to extend the row to the point where, or by adding a metal frame essentially. This is a metal plate that's reinforced, that's got holes pumped in it. The goal here is twofold. So one, if you go think back to some of the images Yarrow showed about the stress concentrations along the south edge of the array, that would be mirrored on the north edge. You've got the highest stress concentration, that very intense suction pressure is all the way along the edge of the array. So we provide a steel structure that occupies that space of that high suction load. So this porous panel system does twofold. One, it occupies that space. It causes that intense vortex to apply load to steel instead of to a glass module. And it is also porous, so it helps to break up the formation of that vortex. So by using the system, essentially as you work your way from the edge of the array inward and you look at the pressure gradient, by the time you get to the first true PV module, the pressures are low enough that they can be accommodated by that module. This is a nice system that we're using right now in South Florida in the US, obviously a hurricane-prone location, and that we're looking to use elsewhere, again, as a way to reduce the maximum wind load on any given module. In terms of the tracker or fixed tilt racking structure itself, I'll be honest, there's not as much sexy and exciting to talk about here, but I do want to touch on this. So the row tube design, the post design, should be done in accordance with codes and standards. Right? When we're in Australia, we're designing with 2159 for the posts, looking at 4100 or 4600 for hot rolled or cold form steel. In terms of, or some things to keep in mind, particularly with large format modules. So the longer panels or the longer cord length from the large format modules do mean more torque on the road tube. They typically do get more load at the top of each post. And something that may not be necessarily obvious, but in terms of the reveal height, how much the post sticks up above the ground, for the same clearance, the same distance from the bottom tip of the modules to the ground, and the same tilt angle, a larger format module is going to require more reveal height. The road tube is actually going to be higher off the ground, given the increased length of the module. And that has a couple knock-on effects in terms of more steel for the posts, greater bending moment at the base of the post, so you may have to increase the kilograms of steel per meter, and you may have to increase embedment depth. So just some things to keep in mind when picking a module. And one of the detriments, I know that module change midstream of a project is not uncommon right now, given the volatility of the PV module market globally. But you're designing for a larger module first, and then having to switch to a smaller module is much easier than vice versa. All right. Lastly, Yarrow and I talked a lot about air elastic stability, but I wanted to touch on kind of some of the tools that are available to address that failure mode. So in particular, in terms of damping stiffness, so Game Change utilizes shock absorbers. They're springs coaxial dampers, but the dampers are very, very stiff. We take a slightly different approach to our dampers than most of our competitors. Our dampers are in excess of the critical damping, rotational critical damping of the tracker structure, and that's been verified through plug tests or free vibration tests. And the point of that is that during that design wind event, during that wind gust, the damper will not move. It will act as a strut. So again, we're taking a different approach than kind of conventional harmonic design. We're not using the damper in terms of trying to move counter to the excitation of the structure and pull energy out of the system. If you're trying to use a viscous fluid damper to pull energy out of your tracker through a multi-hour hurricane, it's not going to work, right? The viscous fluid is going to heat up, it's going to lose its damping, it's going to fail. We take a different approach where the dampers are very stiff, so during the design wind gust, they do not move. They're not stiff enough to drag the actuator, they're not stiff enough to drag the motor, but they're stiffer than the critical damping of the system, such that they don't move and they can act as a strut. So we can unload torque from the torque tube, and they act to increase the stiffness of the system, push up our critical wind speed for air elastic stability. So with that, I'll pause there. Thank you, everyone. Thank you, everyone, for your attention, and I look forward to the conversation continuing with some questions.
Thank you very much, Scott. I have heard a lot of presentations on this topic, mostly in Spanish, I have to say, so I learned a lot of vocabulary today. But I really, really liked your porous panels idea. I think it seems simple, but such a great solution, and there are questions on it. So I'm really looking forward to hearing more about it. Genuinely, really, really cool to see. Can I just say, we're a little bit bad on time at the moment. I know we're almost the hour, but you have to admit, it has been such interesting presentation that it was really hard not to just be so interested to forget about time. So we have 7 questions open right now, and my aim is to answer those 7. Hopefully you guys won't be sending another 7 in the meanwhile. If that is okay with you guys, we'll take a little bit more time. If you absolutely have to go, sorry, it's a shame, you're going to miss the fun, but it's all recorded, so you don't have to worry about it. You can watch it after, okay? But I do think that if you guys don't mind and you have another 10 more minutes, let's try and answer those. We are going to have to go quite to the point because, otherwise we don't have a lot of time. And at least Scott has answered 2 of the questions that I had. One of them was about stow positions, and another one was about the larger modules, and you've already done those 2. So let's go with the questions from the public. Okay. How do we consider the scale factor for all the wind tunnel test, since the test is all based on the reduced scales of the structure? This is the first question, and it's for you,
Sure.
Yarrow.
Yes.
I've done my best reading. Yeah, go for it.
Yes. Yeah, it's not a problem. So, the scale factor is inherent in the analysis. So whatever scale was analyzed in the wind tunnel, that sort of locks in how the results can be applied. The data from the wind tunnel can be processed or analyzed for different scales for different size structures, but there is a limitation there that it's not infinitely usable for different size structures.
Thank you very much, Yarrow. It's good that also Scott gets like a couple of minutes off, to recover. So how do you verify that the scale model of the structure is the exact representation of the product at real scale?
Yeah, there's many studies that were done, decades ago, related to the industry of modeling small scale structures in the wind tunnel in the first place that tell us a lot about what details need to be included. But ultimately,
it's not just me, right?
There's usually a little bit of experimentation involved, if not a lot of it, a decade or more for solar structures.
Thank you very much. Okay, this I think is probably for the two of you, but I'll leave it up to your own consideration. Is the next one. For sloping sites, the regional wind speed might be significantly less than site due to the wind speed up. Is this noted in the design procedures? I'm sure it is, but maybe tell us how.
Yes, yeah, it's it is a standard parameter or a part of every procedure in an international wind loading standard to account for wind speed up over topography. It's a little bit trickier with solar, certainly more than we have time to get into here, but the wind speed up part is accounted for in the standards.
Do you want to add anything there, Scott? Because this has got a lot to do with the complicated aerographies. They're difficult to design and procure.
Yes. Yeah.
Scott, do you want to add anything here?
No, not too much. It's a little bit of a Pandora's box to start diving into. As Yarrow noted, all major standards have rules about wind speed up over escarpments. Typically, it's not applicable for most flat or most sites for solar are still flat. As we use up all the flat ones, that may change. We may start to deal with more projects with ridges and escarpments. But for now, we're still using the values in ASC 7 or Eurocode or what have you.
Thank you very much, Scott. Okay, the next one is about, it asks you whether your design target is V50. And here, this person believes that or thinks that this is a bit too low for a 35 years design life.
Yeah, this is for a 25-year design life project. So you are correct. If the design life of the project is longer, then the V rating would increase.
Excellent. That's clarified. Okay, we still have 4. I don't know how this happens. They're multiplying. Okay. Do terrain angle and wind inflow angle have an impact on the torsional stability? i.e., are trackers on undulating terrain more or less prone to torsional instability than trackers on flat terrain?
There are a few aspects of that are important. One is the wind speed up in terms of terrain angle. So if there is an increase in the wind speed, that certainly matters as far as the stability is concerned. The second one is the relative angle of the tracker to the terrain. So that relative angle may be significant depending on where it is on the slope. As I mentioned, there's a specific low tilt instability and a high tilt instability. And that terrain angle matters in terms of the way the wind sees the tracker. And then I think the last part of the question was the wind inflow angle. And absolutely that has an effect as well. For a perimeter row, having a slightly off angle approach wind can reduce the effect, but for an interior row, it can actually be slightly worse because they'll tend to go unstable when the wind is cornering and has more of an open approach to the end of the row.
Thank you very much, Raro. I have to say, guys, if you have a complicated geography project, please see like specialists, because there are a lot of specialists that they actually design, and they model because it's easy to get it wrong. Just say, there's so much to learn still, and especially you can spend a lot of money by making the wrong decisions in a complicated orography. This is a topic that we've covered a lot in Data Insights, so you have a lot of literature if you want to, look for this kind of thing. We've done tons and tons and tons of work on this. Okay, so next, what is the wattage rating of the porous panels? See, this is like a question that I want to follow up on.
Yeah, so the porous panels are just steel. They are not a PV module. So there's no DC output, unfortunately.
Yeah, I mean, makes sense, to be honest. It's just a way to make it stable, because in the end, you have that road, there's in the perimeter road that is actually not being moved, and therefore not moving the whole. It makes sense. Right. How important, but maybe there is a business model here, guys. Just saying, it could be an idea. How important is the effect of fatigue on the connection?
So in theory, these connections, I'll keep this conversation specific to bolt and nut connections, which are appropriate for a cyclone-prone system. If you're doing a clamp type system, it would be a different conversation. But for a bolt and nut connection where both faces are flat, the fatigue should not be an issue in that you're never exceeding the preload. There's no joint separation. If your surfaces are not parallel, the bolt's in some sort of bend, if the bolt is in free air, that becomes a much bigger concern.
And the last one that we have here, you guys have done really well because we've gone through a lot of questions really quickly. It says how to convert 3S. I don't know how to read this properly. You guys can correct me?
3 second, yeah, 3 second gust.
3 second. 3 second gust wind speed to 0.2 second gust wind speeds.
Yeah, there are a few approximate methods, but there are more accurate methods as well. We have a fairly accurate method that relies on the turbulence spectrum to give you that conversion. There is a published method in ASCE 7 in the commentary. I know it was, I think 716. It may have been in 722, but yeah, there are some published methods to do that conversion, so that you can go back and forth between the different standards. Okay,
and finally, if I can ask you again, the question about the larger modules, because you've both talked about this, and I know it's a big deal. It's changing everything essentially. If I am a developer, what I want to know is if I'm a developer that I'm considering like larger modules, what do I need to take into consideration if I am like in a high wind areas? Like, how difficult is my procurement? How difficult? How much more difficult is my design? And what does it mean in terms of what I can really make extra in the, if you just give me like a cost opportunity there analysis really quickly, in 1 minute, Scott and Yarrow.
The biggest thing is going to be talking to that module vendor, getting the mechanical rating of the module, and then turning around and handing that to your tracker or racking vendor, making sure that the module is strong enough for whatever site you want to put it on. That's the most important part of that decision.
Yarrow, anything to add here? Some words of wisdom?
I think Scott summed it up well. If there's an advantage to going to a bigger module, you have to consider the difficulty in mounting it. So it's sort of a balance. And Scott would certainly be the person to talk to about how to manage that and how to handle the loads, because the loads get worse as you go to a bigger module. Okay,
so thank you very much, Scott. Thank you very much, Yarrow. It has been a lot of technical detail. It isn't easy to absorb everything at once. There is so many technical aspects that get into the physics, of wind, which is extremely complicated process. So you're forgiven if you haven't understood everything 100%. I have seen, similar things many times, and it's so difficult for me to still keep track. So I am sure that you've enjoyed it, because I've seen a lot of people asking the questions that even take, the effort to read. So thank you very much for being there, guys. These two people that you see here are absolute experts on the topic. So what I would do if I was you is get their email, they're in the presentations, get in touch with them if you have questions, if you're considering these kinds of complicated projects, because it's best that you have the best information and you're working with the best people that know how to resolve the issues that you're going to encounter. So this webinar is not only for about information, it's also about networking. Today everyone is an email away, so I just like to remind you all that you can always reach out to Scott and to Yarrow for further inquiries and also for business deals. So thank you very much, everyone in the audience. Thank you very much, Scott and Yarrow, and see you next time. Thank you very much. Bye. Bye.
Bye.